everyone, welcome back to our YouTube channel, Becoming a ROS Developer. Today we have a presentation for one of our courses. This is ROS Basics in 5 days. And at the end of this course, you can take one of our projects, which is actually implemented on a real robot. So that's what we're going to be seeing here today, that project for that course. And our student Mikhail is going to show us how he solved these problems, this project that is specified in our course, ROS Basics. So hello, how are you?
Hello, thanks for introducing me. I'm good. How are you doing?
I am great. I'm very excited to see your presentations. So whenever you want, please share your screen and just show us how you have managed to finish this project.
Okay, then let's start.
Great.
I will start with the live demo.
Awesome. Yeah, we can see your screen now.
Yeah, great. So we have robot already. Let's move it to some position. Yeah, there. So we can test fighting wall service properly. Okay, I think this will work. Yeah, I need to start all these things first. I think it's already built and configured, so
yeah, it'll be built.
What's the name package? And let's go.
It's the little antenna. You see that next to it? Right there, yeah.
Yeah, so now it tries to find the wall. When it finds the wall, it rotates. And then the main cycle starts to execute. At the same time, odometry has started, so it will collect all the odometry data and calculate the distance traveled by the robot. And when the robot will finish the lap, the odometer will stop and tell us well, how much meters the robot has traveled.
Awesome. I also saw that you started it close to the obstacles. That's awesome.
Yeah. So wall following behavior is pretty simple. It just reads the distance to the right of the robot, and if the robot too close to the wall, it steers left. It's too far from the wall, it steers right. And if the robot is in the right position, it well, goes straight. Also, to reduce the wavy movement of the robots, I implement a little bit of correction that the robot steers more if it closer to the wall or too far, and when I went closer to the desired position, it steers less aggressively. So it helps robot to follow more or less, not so wavy.
I see. Do we have any output on your terminal where you launched your programs?
Yeah, we have some logs. Those are mostly for debugging purposes, I should say.
Do we have a feedback of how much the robot has traveled?
Yes. So we have logs from wall following node and from the odometry action service.
Yeah, this delta.
Yeah. So we actually have feedback. Yeah.
I see. I see the feedback. Yeah. Yes.
this some debugging information.
Uh-huh.
So now robot approaching its starting position, and somewhere soon it should stop the odometry.
Maybe it already did it. Was the
No,
robot supposed to stop or?
No, robot will continue, but the odometry
Okay.
will stop. I think it missed the starting point, probably.
Oh, I see what happened. Okay.
Yeah, so margin is not that big, so it could drive through,
Again.
not the catch the starting point. Yeah.
Okay. Why don't we just let it running and see if it catches it, and
Yeah.
then you can go a little bit deeper into how you've managed to do each one of these sections.
Yeah, sure. So the project consists of three major parts. It's wall following node that has the main logic for wall following. Then there is node for find wall action. It's a service, and another one is odometry recorder that records the odometry. So let's go the following node. Yeah, so first of all, it has publisher where then this node publishes node steering actions. Also, it is subscribed to laser scans to read distance to the obstacles.
Mm-hmm.
It has a client to find wall service to execute action of finding wall, and also it has action clients to ask action and then reads feedback from the odometry recording action service. Each of those services has its own callback group. It's a mutually exclusive callback group, but it's unique for each of these publishers and clients. So any of those callbacks could be executed in parallel. Then some settings of laser readings. Well, real and the simulation differs a little bit. The laser settings, I mean. And well, about this I will take a little later. So everything works within laser callback. So this callback is executed whenever new laser readings is done. And first of all, we want to run found wall behavior. So for this, I utilize wall found variable. It is false on the start, and whenever this action is executed, it's then well, true, and this section is skipped. So all starts with the calling. Wait, where is it? Yes. Calling client. Client, I mean, client of the findable source requesting, and after the wall is found, this variable sets true, and then we can start recording odometry. Also, we can check whether it's done finally or.
It might be hard to find it.
No, it's still.
What you could do is either change that, make that bigger, you know, the initial position. I'm assuming you're doing like a radius or something, right?
Yeah, so it missed once again, but probably it will catch right now. Let's see.
No, because it'll continue to drift, so it's going to be harder and harder, I think.
We can try to restart, and hopefully it will
Yeah.
find this nice spot. Okay.
Yeah, and if not, you can show me where you do that in the code. So
No, it's not the wall. Okay, should I proceed trying to show you this, or I can?
well, what I would do, quickly go
Mhm.
into your code, increase that radius, and just run it again. And if not,
Okay.
I mean, you can just show me where this happens because it is one of the requirements, let's say.
Mhm.
So somewhere you have like where probably the autumn recorder, yes,
Over here.
where you would say, "Hey, get the result."
Yeah, this one. Oh, this line is
Isn't that? Yeah, I
five,
think that might be it.
5 centimeters.
So you can put 20, I don't know, 25. So it's surely going to
Mhm.
catch it. You will need to rebuild quickly and then
Mhm.
launch it again.
Yeah, meanwhile, I will set the robot to some position. Yeah,
Mm-hmm.
this works.
So this moment, did it find that wall over on the top? Was that the service completing?
Yes, it was the service. Yeah,
So it picked a wall that wasn't the closest one, correct? Or was it? I didn't really.
should be closest.
I mean, it worked, so it's good.
Yeah, what is this? The index. Anyway. Yeah, while it is going in circles, I will continue with the code.
Mm-hmm.
Yes. To prevent entering the laser callback many times, because it's executed every time the new reading is ready. So and the wall is not found yet. I put this section. So and this indicates that currently we are in the process of finding the wall, and wall is not found. So we simply do nothing and return from the callback. So after the wall is found, we can execute finally the steering itself. So here I set a message to publish to yeah, cmdval topic. I set linear speed and angular is 0 for a while. So here I get a distance to the wall on the right side of the robot. And this multiplier is this factor I mentioned to reduce the wavy motion of the robot. It simply reads a little bit right and a little bit left from the well, exact right position and calculates difference between those two rays. So when our robot is twisted, one ray is longer than the another. So that means it is not exactly parallel to the wall.
Mm-hmm.
Yeah, so if robot is straight within well, some margin, it goes straight. If it is closer to the wall, it rotates a little bit. If it is no, yeah, if it is starts to steer away from the wall, it rotates to the wall. And in some other cases, so it will steer not that violently. Yeah. And yeah, then I published the message with the speeds and angular velocities, and yeah, that's this callback executes again and again and again. Let's check my robot. Did it execute the whole? Yes, I think it is did one lap.
Yeah, the problem is that this terminal isn't infinite.
Yeah. Yeah, this keeps it. Well, the odometry service stops publishing its logs. That means that it executed
Right.
and finished. Yeah, but do you want to see those final results?
I would love to. So maybe like leave a window open so we can catch it.
Okay.
See, this is the behavior I was concerned about. Right there. So right now
yeah,
it's following the obstacles as if they were, which is cool actually, because it might actually do it, but it's gonna start. Yeah. So you should probably stop this.
No.
No?
Yes.
All right. So we have around 5 minutes left. So I would love to either see this or see how you've done this in your both your server that we haven't taken a look at and your both servers, service and action server.
Okay, so start with the service probably. It also has publisher to TMD Velocity and has subscriptions to laser scans. That's pretty simple. Whenever the action is called, not action, sorry, service, it will find the minimal distance in all ranges, and then it will this is index of the reading. It will follow to that direction for a certain amount of time. So it is, well, not probably the best implementation. It should probably stop by laser scan. But anyway, this time is calculated, basically. No, wait. First it will rotate to the direction of the wall. Then it will go, yes, until the reading of the straight will not less than 0.3 meters. After that, it will rotate parallel to the wall, and it will return response saying that's well found true. It's a custom message built specifically for the service. Yeah, that's it. And the laser callback simply updates the variable with the latest laser. So how's Roman doing? Did you miss that again?
Yes,
Yes.
That's fine. This isn't gonna happen, so you can just show me in your code.
Okay. Then odometry recorder is an action service. it reads from a DOM topic, and oh yeah, that's basically it. So this callback is called when we update it on a DOM topic, and it updates variables with the robot position. Then execute callback is called whenever we ask to execute our goal. Or yes, so we update our initial position first to get to know when we need to stop. Then it creates a feedback message, and in the circle, in the loop, we update this feedback message and send it back as a feedback. This feedback contains currently total distance traveled by the robot. And this is calculated as square roots of the previous readings of the odometry and the current readings. As a distance. We send this feedback, and so then we check if we returned to starting point with this margin, and whenever we did this, we break the circle and mark the goal as executed and send final results with the list of all the readings we had, and that's all. Final results. Yes, only this. Yeah, this is the node that records odometry.
Awesome. So that's it, right?
Yeah. So yeah, in the world following, we have also a bunch of callbacks to process odometry, and it's not that much of interest there. Yeah, that's all.
Right. Okay. Right on time. Thank you, Mikhail. Congratulations. Very, very nice presentation. So let's go. Oh, look, right on time.
Yeah.
So let's let me just switch back here to. All right. Great. Congratulations. I got a couple of comments that I noticed. So let me. My first question is the easiest one, the one we kept running into it. You probably can answer it. How do you avoid the action result not returning?
Action result not returning?
Like you wanted to return every time. How would you do that? We saw that it missed it a bunch of times, right? After one lap, we didn't see that result. How would you make that happen?
So result is sent is just too many messages in terminal. So we could reduce amount of logging we have, or like set different
what
logging
I mean,
levels.
Though, is that sometimes the action is not returned. Or you're saying every time it completes a lap, you will for sure get a result?
Yes, whenever this
no, it wouldn't. If it misses that radius of 0.5 that you changed, 0.05, correct? Unless I'm misunderstanding. So let's say how do you check that the lap has been completed, basically?
In the action service itself?
Yeah, how? How do you check?
I check the position of the robot, that it is within the radius of initial starting point.
Right, and that was 5 centimeters.
Yes.
Right? So basically, sometimes it might not do it because, it might be running around and it might miss that radius. My question is, how do you ensure it'll always complete? Because we can see that sometimes it might not.
Yeah, we can set, for example, some timeout, and if this timeout, we can check this time and
Yeah,
abrupt the action and return that's the false result.
yeah. Or make that bigger, which is what we did, and make
Yeah.
sure, afterwards you can, the process is done, stop the robot and kill the node. So that way we don't have to scroll up and try and find that result
Yeah.
of the odometry points. Okay, and then 2 comments I saw. The first one is that I saw that in the wall following node, you do everything in the laser callback. And actually, I do not recommend that because you actually did it correctly in the servers, right? You just got the message and that's it. That's what you should probably do most of the time with sensor callbacks. Why is that? You might have noticed, I even saw maybe your concern a little bit in the beginning. It was getting way too close to the wall, right? And you set the range from 20 to 30 centimeters. It was actually a little closer than that, I would say. It was closer than 20 centimeters. And the reason for that, I believe, was that your laser callback hasn't completed yet by the time a new message arrives, a new sensor message. So you can just, for whatever reason, something in that callback can get stuck. And by the time the new message comes in, you might be like too close. It's like, oh, time to correct. And it was too late. So that's one recommendation. You did it correctly in the service. So I encourage you to do that across the board for sensor callbacks. And the comment about, we saw how the robot went towards a obstacle and started trying to go around it. And then you showed me the service server and it explained why, right? Because you catch that minimum distance, then you turn towards it blindly with time, and then you move forward. So I didn't know if the moving forward was actually was that with time as well? Or was it receiving new information from the laser? Once you
receiving new information.
Forward. Okay.
And,
yeah. So that straight variable is that that's updating. Yeah. Okay. Yeah. So that's updating the ranges of the front one. So you should probably do the same when you're twisting. Of course, in this scenario, it would also go towards the obstacle because it was the closest one. Then you can do little filtering to avoid that. But my point is that you're always want to avoid driving the robot blindly because in reality, a million things can happen. And this is one of the things from like normal software to like robotics. It's like you switch to the real world, and in the real world, all these things can happen that, you might be able to go around it with sleeps and things like that and times, which is good. But what if the robot, finds a little stone on the wall, or like maybe the motors aren't as precise as you want, so that time isn't precise. So it's not 90 degrees, it's 85, right? So that's why we always do the sensors to obtain that information and correct based on that. So that would be my two most important advice. One is leave the callback as lean as possible, so you always get all the data you want because that's what you want, and don't drive the robot blind. So
okay, thanks for the feedback.
Yeah, other than that, Mikhail, congratulations again. Really nice project, straight to the point. And besides a couple of little details there, I think we can see that you took all the learnings from our course, and I just want to say congratulations.
Thank you.
All right, guys, let me switch back to my screen. And yes, this is what you can do when you take one of our courses that offer a certificate, is come and try and present what you've learned on a real robot to showcase your learnings. So I invite everyone to do what Mikhail has done here. And yeah, guys, that's it for us today. We'll see you for the next video. Bye-bye.